Lastly, in section 3, we talk about other kind of confidence intervals. Right? Because if you go back to the previous section, you see that the interval, that there are several requirements. First, okay, we get x bar from the sample, right? But another another requirement is that the standard deviation must be known by some sources, maybe it's by magic, right? And also we kind of assume that this whole thing, follow the normal distribution. And that's a big if. I think that has to follow normal distribution. Because recall that when we talk about distribution, there are lots of ways you can make distribution. You can make a curve that looks like that. That actually has a name called the geometric distribution or Poisson distribution. You can have an uniform distribution. You can have, any sort of distributions. But for this to work, we have to, assume that it is normal distribution. And here we could kind of assume it is normal distribution because we talk about the mean. And by law of large number, the mean is close to the normal distribution. So that's the requirement behind that. But if they don't follow normal distribution, or if sigma is not known, or if we talk about something else that is not the average, then maybe we talk about the proportion, we talk about the standard deviation itself, then what do we do? And the answer is we take a look at different formulas. And there are two separate sections here. First, formulas and how to apply them. Second, how did we get the formula in the first place? Here we will focus on, the formulas and how to apply them. But the origin of the formulas is a different story for another time. So the first formula, this is when we want to find the population mean, but the sigma is unknown. Maybe this is the first time you do a survey on this topic, so it is impossible to know what the standard deviation is in the first place. In that case, we actually have to use a different distribution. If you don't know sigma, then this distribution is no longer the normal distribution, and this is actually called a t distribution. And since it is a different distribution, then it has different table, it has different formula, it has different app. So in practice, just make sure you use the correct formula or the correct table to compute that. But nevertheless, the formula is still, familiar. We still have x bar. This is still the sample mean. But this t alpha over 2, this confidence level needs to be computed from the different table. And there's something different, slightly different, because previously we used sigma, and we used the population standard deviation. But if we don't have that, if you don't know the standard deviation for the population, then we need to stick on the sample standard deviation instead. So get a sample and by standard deviation from that sample. So of course there's more work to do. We need a different table, we need a different standard deviation. But nonetheless, if you apply the same concept, you use the same kind of computation, you can still derive this formula. And yeah, let's try that. Let's suppose we have this one. Suppose we have a sample size of 20. And we know we have the sample mean of 175. But suppose we don't know the sigma. The sigma is not given. And we have to find the standard deviation ourselves from the sample. Suppose that happens to be 10, then we can still find the confidence interval. And actually we still have to follow the 5 steps. In the first step, like now the first step is more important because we now have to identify everything ourselves. So in the first step we have to say, okay, since the population standard deviation is not given, then we assume that this follows the distribution instead of the normal distribution. I think that's off the screen a little bit. We assume that this follows the distribution, and you need to consult or you need to look up the t table instead. And also, this is a good place to recap the numbers we have. N is 20, x bar is 125, s is 10. Sometimes you have to do this yourself in this step. Here they are. 9. So 1 minus alpha is 0.95 because we are looking at 95% confidence interval. So alpha is 0.05. And then step 2 and in step 2, and 3 and 4. Not just use similar idea. But here in step 2, right, we have a different table instead, so we're gonna have to look at a different curve. It's gonna be the t distribution, but the same idea applies. We find a point, this point where the area to the right of that point is alpha over 2. I think I make a typo. Here n is 20, here n is 20. And after you get all these things, the value of t you get is 1.684, which happens to be close to the number we got above for 90%. But here is 95% for different table. But eventually, you're gonna plug everything into this formula. That's 175 plus minus 1.684 from the app or from the table, from whatever you use, times that number. And in the end is about 171.24 to 178.76. That's step 4. And step 5 again, just write down your conclusion of what that number actually is. Is that how you pure confidence interval for a different type of distribution, for different type of problems with different requirements or different given values? And everything else will follow the same, that's the same line of reasonings, not just different formulas. And then we have a confidence interval for population proportion. And now we want to ask different questions. We have a question about the actual proportion. If you go back to the bins example, like in the first section, here we want to know the actual ratio of the blue balls in this box. I think it was like 0.9, I think, which is very high. And here we can accomplish that by using this new formula again. It's just another formula. But there's also a reason behind that. We have to first identify or understand or prove that P, this P actually follow the binomial distribution. And the binomial distribution for a large sample size or a large number of trials could be approximated using the normal distribution. And once you have the normal distribution, then luckily, then we can get back to the C value. And this means for the proportion, we can use the same C value as we did before, which is for 95% confidence interval, you use 1.96. For 90% confidence interval, you use 1.64. For 99% confidence interval, you use 2.557. Because we have the same confidence, or we have the same distribution. And another thing to note is that once you have the P, and once you have the sample mean, we can actually compute the standard deviation from the sample mean itself, which is this formula. But at the end of the day, the final formula looks like this. We still have the P bar, the sample proportion at the starting point. Then we increase or decrease it by the margin of error. Okay, let's see a quick example of that. Yes, so suppose we get the actual balls. And suppose your bag has 150 balls, and the sample proportion. Sorry, suppose your bag has lots of balls, and you take 150 balls out of those bags, and then you get the ratio of 0.4. To estimate the population proportion, and then use 95% confidence interval, then we simply apply that formula. And again, you have to follow the 5 steps. But here, the step 1 is actually some requirement. We didn't talk about that, but the requirement is that n times p must be at least 30. It's actually required, but let's say we skip that. Let's say, oh, that there are enough number of balls that we can use this formula. And here the formula p hat is 0.4. The n is 150. And again, 1 minus alpha is 0.95, alpha is 0.05. And then the confidence level, the C value is 1.96. And finally, in step 3 and 4, then we can use the formula to derive the interval. It's going to be p plus or minus z value, and the formula is a square root p hat times 1 minus p hat divided by n. And this n is inside the big square root. And p is 0.4 plus or minus z, that is 1.96. And then the square root of p, which is 0.4, 1 minus p hat, which is a 0.6, divided by n, which is a 150. And if you do everything correctly, you should get 0.4 plus or minus 0.078, which gives you the interval of 0.322 plus or minus 0.478. And so that's the result. So here the conclusion would be that we are 95% confident that the actual or the population, in this case we are dealing with the proportion is inside this range. So that means if the ratio of the balls we got from the bag is 0.4, then we are pretty confident that the actual ratio of the balls are 0.322 or 0.478, or numbers within the range. And now this gives you a good idea of what the numbers are actually. Oh, that's the proportion. And this formula is actually pretty useful, because in theory, if you have games or you define things, most of the time you care about the proportion or the success rate or the drop rate, those kind of values, more than you care about the average. And so in practice, this formula is used slightly more frequent than the other one. And lastly, we talk about the population mean, we talk about the population proportion. Of course, we can talk about the population variance, population standard deviation. Our variance should be sigma square, my bad. Right, but the formula doesn't look friendly, I would say. It just looks kind of bizarre. But just to give you a complete list of formulas, I'm not gonna have you to do this in test. But to give you the complete list, right? There's a formula for that. And the formula is slightly more complicated. We have n-1 on top here. We have the sample variance square. And we multiply these two together, and we have the chi-square distribution. We're gonna actually talk about this in the last lecture. This is actually also another useful distribution to have, to keep in mind. But for now, we say, this thing follow a different distribution that you can look it up on the internet somewhere. And if you look this value up and plug everything into the formula, then you can derive the confidence interval for the population variance or standard deviation. And lastly, sometimes you have two groups. Or not sometimes, most of the time, if you want to conduct a study or you want to conduct some surveys, usually you need to divide people into two groups. One is a control group, where you just ask them to do things in the normal state, and you have the experimental group, where you fiddle with them. Maybe you ask them to drink tea before finishing exams, or you give them exams that are more difficult or have some funny things inside. And you want to compare, whether whatever you do to them, make a difference compared to the control group. And so whatever you do with these two groups, usually when the final number that you care about is the difference between their average. So for instance, you want to see whether people who drink tea will do better on exams. So the first group, the control group, is the group of people there who just do exam normally. And then the other group is people who, you give them tea before they do exams. And once you finish the experiment, you get the average scores of the control group versus the average score of the experimental group. And you want to see if they have significant change. So it is true that people who drink tea before the exam do better, get a higher score. And on that kind of experiment, you are looking for this number. And that number, then need to be put into the formula, just to see whether that actually make a difference. And the formula here, again, it looks the same. We have the number, the actual number, which is the difference between the mean and the confidence level, and then some margin of error. Previously, we have sigma divided by n. But now, since there are two groups, then we have two sigmas, two n's, two sample size. So the way to combine them is using this formula. And at the end of the day, you get a interval of the difference. So this is the third kind of not the third kind, but the different kind of confidence intervals that you might use in practice if you have to conduct a research. Okay, so that's the end of the author confidence intervals, right? I think there are 4 in this section, right? But the proportion is most popular or most prevalent, right? Everything else, just take a look at them and see. Sometimes in the future we might need that, but not a lot. And and there's an extra section. And this discuss the meaning behind behind this one, behind the confidence interval for the proportion. Like we have some proportion. We take some samples and we find the interval that we believe it is. Right? But in if you translate that into some specific types of problems, right, it is like asking for the probabilities of probabilities. Right? Because we have the interval of the proportion. And the proportion can be thought of kind of a way of probability of the ratio. And in this interval give you a chance, give you the confidence value, the confidence level of count of that probability. So in a sense, it is a probability of probabilities. And this is this link, this clip, which is from my favorite channel, 3 Blue 1 Brown. You can see that that icon over there. This is trying to answer the question of, suppose you are going to some popular marketplace online, like online shopping website, where there are you find 2 different shops. Right, the first shop have, let's say, you say, okay, 48 out of 50 customers are happy with the purchase. Say, oh, actually this one, there are 3 shops. Right, the first shop say, okay, every single person are happy with their purchase. The second shop say, okay, 48 out of 50 people are happy with their purchase. And the third shop has, out of 200 people, like 186 people are happy with their purchase. And the question is, which shop is better? Which shop should you buy from? And that's the the question. But because at glance it seems that, oh, this shop must be the best because 100% of other people are happy with the purchase, and so that must be the best, right? But the thing is, you can see that the sample size are small. Only 10 people rate that shop, so maybe there are 10 friends. Like I open a shop and I ask my 10 friends to, okay, give me a positive rating of my shop, and so that 100% needs to be taken as a grain of salt. Now there could be some error for that. Right, versus the second shop where, okay, there are lots more people, and of course that based on this number there are 2 unsatisfied customers, right? But oh wow, 48 people of these 50 people are happy with their purchase. And so maybe you have to weigh between, okay, do you want to look at like 2 angry customers or 48 satisfied customers? And how do you compare that shop to the first shop, where everyone is happy, which is not that likely, and versus the last shop where you get a lot more customers with slightly smaller rate if you just look at the rate itself. And the answer is, there's this Laplace rule of succession, where you can compute the expected, this is the expected the value for the actual proportion. Oh, and yeah, but by the way, these numbers that we got from the shop are just samples. It's a p hat. And because again, we are not asking for every single customer to rate the shop. Only some of them rate the shop. So that's just a sample. Right, and we are trying to find the actual mysterious population proportion. Are people actually happy? Or are they unhappy? But they just happen to, pick happy customers to represent the shop. There's a link under this file if you have the file. But if you don't have it, then I think I can, if I don't forget, put it under the description of the YouTube. And so yeah, that's the end of this lecture about confidence interval, of how we can apply the knowledge of the normal distribution and translate that in terms of how we make an estimation using some kind of confidence level. Yeah, see you next week.